Well, thank you very much for joining me here. We're here to talk about the TFA 9895. This is our second generation of algorithm for speaker boost. So I'll introduce a little bit about the general products and their success, and then I'll go into a little bit of the specifics on exactly what the TFA 9895 does that's brand new. So first, I want to give a little background on audio here at NXP. So we're coming up on 100 years of audio experience. That's more than any other semiconductor company can say. So in the early 20s, Philips Electronics would have started working on tube amplifiers and radios. So that same group then went on to develop the cassette tape, to develop the CD, and to develop many other groundbreaking things in audio technology. And when NXP was formed in 2006, we took all that expertise with us in the form of a research group that's based in Leuven. So we were started with this foundation of audio expertise. So I'll try to keep slow. So one of the key things is that we had research engineers who understood not just electronics, but also the mechanics and the physical acoustics. So in 2010, we formed a product line specifically to take advantage of this. So we took a group that was dedicated to Class D amplifiers and low power, and we specialized and focused on solving the problems for micro speakers. So I'm talking about 1 cc, very small speakers for mobile phones, tablets, portable devices. We're headquartered in Nijmegen in the Netherlands, but we have research groups all over, including the R&D group from, that was part of Philips, and that's based in Leuven. About a little over a year and a half ago maybe, we launched the TFA 9887. So this was our first product that featured adaptive speaker boost. And then we're continuing to invest and grow the group. In 2013, we actually acquired an entire group to specialize in codecs. So this first group of products has been a great success. So in the first year, we shipped over 20 million units. Some of the design-in partners are there on the table, and they feature really prominent names in the business. Just at the beginning of this year, we introduced the second version of the product, where we upped the power. So we went from an original 5-volt boost to a 9-volt boost. And both of them were able to provide more power than anything else on the market. So today we're here to introduce the second generation algorithm. So we took the original algorithm that's in all these, and we've made it even better. So as I mentioned, we had great success. So we have a very broad range of products shipping in the market, mostly handsets, and the gaming platform that's here. And the key thing for this is what we are talking about in the heart of our technology is speaker protection. Okay, we're able to put a lot of power in without damaging the speaker. And this is the proof that it works. These are shipping in the market in high volume. There's no issues with speakers. So what does this product do for cell phones? This product is really focused on making the sound better. So we're able to eliminate clipping in the amplifier, and we're able to eliminate clipping in the speaker itself. And it's quite revolutionary. Before, audio amplifiers were only focused on the electronic signal. We're focused on the movement of the speaker. As a result, we're also able to make things louder, considerably louder. In most cases, we get original first generation products raised by 8 dB, The new product can get a little bit more on top of that. We're also able to get much deeper. So these small speakers have a very hard time producing low frequency. And because of our technology, we're able to get everything that the physical speaker can do. And most of all, we do it safer. You could do these things before our product. You simply turn the volume up and up and up and up and up, but you'd blow the speaker up. And it was actually a major problem for cell phone manufacturers. So we've solved that problem. So we don't have the speaker returns. So our first product, at the heart of the product, there was a few key things. So the first was a Class D amplifier, which many of you will be familiar with. It was linked with a boost amplifier. So this allows us to take a battery voltage at 3 volts and move up to 5, or in the case of the other product, 9 volts. So that gives us extra power to put into the speaker. But then we integrate current sensing into the amplifier. So we're able to see the current and voltage exactly as it's flowing into the speaker. So we use that information to build a model of the loudspeaker. Okay, so this is able to tell us exactly what the speaker's doing. We use that to drive a boost algorithm. So this is an important difference from other systems. Other systems will look at the incoming electrical signal, and they'll maximize or try to make the signal fit to an electrical envelope. We're actually doing that on the speaker. So we're making sure that the signal fits the maximum movement of the speaker, and not just the electronic levels, because the electronic levels and the physical movement don't always match. So with these small speakers, the key is getting more power in, right? We want to put power in so that we can get better quality and more volume out of increasingly shrinking spaces. So typically these systems, the speakers are rated for 500 milliwatts, so about half a watt. And normally they'd have to take out the low frequencies, everything below 1 kilohertz, to prevent over-excursion. So it leaves it sounding very quiet and very flat, or tinny is the expression. So there are 2 big problems we're trying to solve. Number 1 is temperature. If we put power into the speaker, that causes heat, and the heat needs to be dissipated. If it isn't, it actually will melt the speaker. So the voice coil literally falls right off the speaker. And obviously that's a failure, and the speaker comes back. Now you can try to predict this. You can, in the phone processor, you can write an algorithm which will predict the temperature in the speaker. But it's not always accurate. Okay? It depends on the ambient temperature. It depends on how long the music's been playing. It depends on specifically actually how much air is coming in and out, because the air coming in and out of the speaker cools the speaker down. So if my speaker port gets blocked, all of a sudden the air isn't circulating, and the temperature goes up very, very quickly. So if I do a ringtone with very high frequencies and I can put in power, within a couple seconds you can melt the speaker. The other big problem is excursion. So what I mean by excursion is how far the speaker moves inside the speaker box. There's a limit, obviously, to how far it moves, and if it goes too far, it starts to stretch and crack. And after a while, those cracks will actually just fail, and the speaker will no longer align properly, and again, it's a failure. So typically, a phone speaker has a resonance around 800 hertz. So the solution up till now has been to simply remove all these frequencies. And that's really why these speakers sound so thin, because there's no bass being produced. once again, you think, okay, well, I could put in a filter to reverse that and just try to balance it out. The problem is that that peak moves. So once again, if I block the speaker, that peak will move. If the speaker heats up, it moves a little bit. As it gets older, it moves a little bit. If it's cold, it moves the other way. If as the phone starts to get old, it may leak a tiny bit, and that moves it again. So it really becomes very difficult. So up till now, they've just cut them out. So the key to solving this problem is feedback. Okay? So we use this integrated voltage and current measurement, and we build a speaker model that adapts. It changes to the environment. So we're watching the speaker in real time and updating the algorithm. So we're able to very accurately measure the temperature, the excursion, which gives us this resonance frequency issue. We're also able to monitor other things within the amplifier. So we can monitor the DC to DC converter. So as the battery gets lower and lower and lower, you don't want to pull a bunch of power for the audio and reset the phone. That'd be pretty bad as if you were listening to music and it just kept shutting your phone off. So we're able to monitor all these things and make sure that we get the best sound no matter what. So I'm going to break away from the presentation, and I'll actually start the demo board. And what we'll be able to do is show you this feedback. So these are two typical cell phone speakers. And what we're looking at is the interface. So our algorithm is fully embedded on the demo board. The computer is just providing the sound source, and it's reading back the information from the algorithm. So what we're looking at, this is the gain being put into the system. So you can see on average, we're putting in considerable extra gain into the signal. This is the important one here is excursion. So this is the excursion limit of the speaker. So that's as far as it can safely move. And you can see we're pushing it continuously right to the edge and not beyond. We can see the temperature is moving around a little bit, but it's pretty safe. We're not really getting close to the limit. And this is the clipping in the amplifier itself. So we're able to drive the signal, and you can see the indicator means we're using that to limit our signal. So we're evenly going back and forth between driving it to the limits of the speaker and driving it to the limit of the amplifier, which means we're getting the most out of the system. And the key is down here. This is the excursion model of the speaker. And what we'll do is change the environment. So I'll block the speaker, and you see the system recognizes that and changes the protection. So I can switch it back and it'll readapt, and the other side will change independently. So we're doing this by watching the power flowing into the speaker. And there's no other semiconductor company that can do this. So they use a prediction. And they may try to measure temperature in a variety of ways, but no one has this constant adaptation and this feedback on the excursion. So what we did was took a bunch of speakers like these in their boxes. We set them up with our algorithm. and we set some without. We put them at the same volume level and let them run. And in only a few hours, and this time 168 hours, we had blown up more than half of the other speakers. So at that point, we knew that our algorithm really did work. And since this point, as I mentioned, we're shipping many, many products into the market. So it's demonstrated that it works quite well. So what have we added? What's new here today? The first product, we focused really on just this protection aspect. And with it came some sound. We were able to turn the sound much louder. Now what we focused on is how do we really make it sound better? So what we added is a multiband component of our algorithm. And what this means is rather than looking at the audio in one big block, we look at it in various sections. So we break it down into a few sections, and we can look at each one separately. So generally, the low frequencies are much more of an issue with the excursion. So the movement at low frequencies, bass frequencies. So we can handle that separately from the high frequencies, which are generally more sensitive to heat. And this allows the sound quality to improve. So the vendors who we work with have been very interested in this. They've been very interested in how do we get the most sound and the best quality sound. Because they believe their customers are listening to the phones more and more media, more videos, all these kind of things that people want good sound. So we also added what's called a noise gate. So as you push more and more power out, you'll notice problems in the signals. So say you're watching a video on YouTube that was very poorly recorded, and it has hiss in the background. So one of the issues is that hiss will get louder. So we've added a device to look for that and reduce it. So as I mentioned, it really focused on sound quality. So if you push our single channel part or any single channel compression very, very hard, you get a problem with the gain moving. So the gain comes down to protect the speaker from these low frequencies, and then it starts to rise to try to boost and get the most out of the lower frequency. And then again, when the beat comes back, the gain drops again. So you get this kind of up and down with the gain, and that's not very desirable. If we break those two into separate pieces, then the first time the bass frequency hits, the gain in low frequency will adjust. And it'll take a much longer time to come back. So it stays stable. And the smaller signal with the high frequencies actually can pump in and raise the gain to the loudest possible, to take all the power that we can deliver. So it's a really nice trade-off that allows a steady gain and better sound quality. And then, as I mentioned, if we play a bad quality signal, so this is basically hiss. The original green line is what a normal system would look like, and with our gate, we're able to detect that hiss and simply take it all out. So things in audio are always a trade-off. So if you want to use this new stability and the new sound quality and push even further, you can. So you can actually push even a few more dB, about 2 more dB out of a system. So as I mentioned, a normal system, we have another comparison that shows the difference here. If you come in with a normal system, you'll have a given frequency response. Then we'll pump in drastically more bass and much more power throughout the whole signal, throughout the whole bandwidth. The new product, we can produce even more. This is a really cost-effective way to get higher SPL. If you can spend a little more money, you can go with our 9-volt product, which gets you even more because of the extra power. So this is a nice trade-off to still get the good sound quality without going all the way to 9 volts.